Hello and welcome. In this video we will look at the relationship between the powers of 10 function and its inverse, the base 10 logarithm. The powers of 10 function, y equals p of t equals 10 to the t, is an exponential function with base greater than 1. Since the growth factor b is greater than 1, we know from our previous studies that p is always increasing, and thus its graph passes the horizontal line test. And from our previous work with inverses, we can therefore conclude that p has an inverse function. That means we know there exists some other function, let's say L, that says the same thing as p, just from a different perspective. So let's take a closer look at what we mean. Let L be the inverse function of y equals p of t equals 10 to the t. Since L is the inverse of p, we know that writing y equals p of t and t equals L of y are equivalent, and they're just saying the same thing from two different perspectives. For example, we know p of 3 equals 10 to the third, which equals 1,000, and we can say the same thing from a different perspective by using the inverse function L and writing L of 1,000 equals 3. Similarly, we know p of negative 2 equals 10 to the negative 2, which equals 1 over 10 squared, which equals 1 over 100. And we can say the same thing from a different perspective again by using the inverse function L and writing L of 1 over 1,000 equals negative 2. We call this new function L the base 10 logarithm. Here's the formal definition of the base 10 logarithm. Given a positive real number y, the base 10 logarithm of y is the power to which we raise 10 to get y. We use the notation logarithm base 10 of y to denote the base 10 logarithm of y. Let's look more closely at how the base 10 logarithm is related to the powers of 10 function. In the powers of 10 function, the input t is the power to which we raise 10, and the output is the corresponding power of 10. If the base 10 logarithm is the power to which we raise 10, then what we're really saying is that the logarithm base 10 of y equals t. And that means the output for the base 10 logarithm is the power to which we raise 10, and the input is the corresponding power of 10. We notice that the input and output of these two functions have reversed, which is an important quality of inverse functions. This emphasizes the fact that the powers of 10 in the base 10 logarithm are inverse functions. Now let's practice using the idea that the powers of 10 in base 10 logarithms are inverses, as well as develop some fluency with the notation of the base 10 logarithm. So again, we have y equals p of t equals 10 to the t, and its inverse function L of y equals log base 10 of y equals t. When t equals 3, we know 1,000 is 10 to the power of 3. And in the notation of logarithms, we can write log base 10 of 1,000 equals 3, which is saying 3 is the power to which we raise 10 to get 1,000. Similarly, when t equals negative 2, we know 1 over 100 is 10 to the power of negative 2. In the notation of logarithms, we can write log base 10 of 1 over 100 equals negative 2, which is saying negative 2 is the power to which we raise 10 to get 1 over 100. On the last slide, we saw that 10 to the third equals 1,000, and we can rewrite that as log base 10 of 1,000 equals 3. We can actually rearrange these equations to see another important relationship between inverse functions. Knowing that 10 to the third equals 1,000, and we can substitute the 1,000 in log base 10 of 1,000 with the quantity 10 to the third. This gives us log base 10 of 10 to the third equals 3. Notice that the original input is 3, it produced an output of 1,000, and then that output was inputted into the base 10 logarithm to produce a final output of 3. All of this to say that performing these two functions in succession results in an output equal to the original input. In other words, the powers of 10 function and the base 10 logarithm function reversed each other's processes. Similarly, we could work in the other direction. Knowing that log base 10 of 1,000 equals 3, we can substitute the 3 with log base 10 of 1,000, giving us 10 raised to the log base 10 of 1,000 equals 1,000. And again, performing the base 10 logarithm followed by the powers of 10 function resulted in an output equal to the original input. So we see yet again that the base 10 logarithm and powers of 10 function reversed each other's processes. We'll wrap up this video by summarizing the properties of the powers of 10 and base 10 logarithm functions. From previous work, we know the domain of y equals p of t equals 10 to the t is all real numbers, and the range is all positive real numbers. Because L of y equals log base 10 of y equals t is the inverse of function p, we know the domain and range will switch. So the base 10 logarithm has a domain of all positive real numbers and a range of all real numbers. Next, we should also mention that 10 to the 0 equals 1, and using the notation of logarithms, we can say the same thing from a different perspective. That is, log base 10 of 1 equals 0. Lastly, we can use composition of functions to say that L of p of t equals L of 10 to the t, which equals log base 10 of 10 to the t. And from our previous work, we know that these two functions reverse each other's processes, and thus this expression simplifies to equal t. Similarly, p of L of y equals p of log base 10 of y, which equals 10 raised to the log base 10 of y, which equals y, because again, these inverse functions will reverse each other's processes. In future videos and work, we will look at the properties of one more important logarithmic function and then use the properties to help us solve exponential and logarithmic equations.